Ingenious minds contrive and measure. With expert judgment and knowledge born of long experience, they select the best raw materials available. Slender strand upon slender strand, the rope grows before your eyes, each skilled process adding to its sturdy strength. With fascinating dexterity, sinewy hands guide and fashion, splice and tie. Supple wires are put to the test by painstaking craftsmen. Every bend, every twist is a test of perfection. Satisfied at last, they throw you a lifeline. It's a rope with strands of steel. Take a look at a steel rolling mill where the history of a wire rope begins. Out of the blazing furnaces comes the gleaming white-hot metal. This is Colville's steel rolling mill, one of many sources of the rods which form the basis for the wire rope. Like a fiery snake, the billet streaks through the rolls, becoming thinner and thinner at every stage on its tortuous journey, till it is half an inch or as little as 7/32 of an inch in thickness. Struggle over, the steel is subdued into orderly coils of metal rods on a railway wagon. Coil after coil is loaded on the wagons and dispatched to the wire works, where the real business of stranding the steel begins. This hive of industry is the rod's destination. At this busy wire works, the raw materials arrive from many directions. All roads seem to lead to its welcoming sign. By rail as well as by road, the materials arrive and pile up. The tracks lead into the rod shed of the wire works, and over them comes a wagon bearing a consignment of coils of rods, each coil ranging up to 400 pounds in weight. Such train loads are arriving daily. They bring grist to the mill. The tracks lead right into the rod shed. There are two railroads here for the busy traffic. Inside the rod shed, they unload the coils of steel rod and check them. They are wheeled off to the store, where they will remain until they are needed for the next process. A busy wire works needs to keep itself well supplied with steel rods of many kinds, with carbon content varying from 0.85% to dead soft. The destiny of this raw material has to be planned skillfully and most accurately. Inside the planning and production office, an order has arrived, one of hundreds. This one is for an excavator rope. To make that rope, wire has to be produced on the most exact mathematical lines. The planning and production office selects the raw material, which is card indexed. They decide how much processing and drawing is necessary to make it into the required type of wire. They decide exactly at which stage in the process the wire must be heat treated. They calculate how the wire is to be reduced evenly to the final size and how the necessary tensile strength is to be attained. Complete data and particulars are handed out to the mill. The planners have worked it all out most minutely, for it is essential that good planning be achieved for first-class wires to be made. They have checked up that the necessary rod is in stock and decided on the process to be employed. The machines are now loaded, and the steel rod threads its way from the swifts into the heat-treating furnace, guided by the carrier rollers. The furnace has a temperature of about 1,000 degrees centigrade. Very close control is employed to ensure accurate treatment. This heat treatment makes the steel more malleable for fine drawing. Atmosphere-reducing gas at the exit of the furnace minimizes the formation of oxides. The heavy normalized coils emerge from the furnace and are now ready for pickling and hosing. From the heat treatment furnace, the rod goes to the pickling process. The bath into which the coils of wire are swung has a solution of hydrochloric acid. This removes the mill scale carried from the steel rolling mill and oxides from the furnace, or rust or other foreign matter. The coils lie in the acid bath till perfectly clean. And so over to the water swill and the high pressure hose. An all-in wrestler preparing for a championship fight is not more carefully handled than the raw material for this excavator rope, which goes from one conditioning course to another. This shower swills off the acid and the loose foreign matter. Then off the rod goes for another dip, this time into a turbulent lime bath. The lime coats the smooth, shiny steel rod to create a bond between it and the soap lubricants through which it will later be drawn. It also neutralizes the effect of the hydrochloric acid and lays on a coat which will enable the wire to be stored for some time without rusting. From the lime bath, the coils are wheeled into the baking oven to drive off the hydrogen imparted in the pickling process and any moisture. Here they stay in hot circulating air at 180 degrees centigrade for anything from 10 to 40 minutes. The higher the carbon content of the steel, the longer the baking. Still loaded on the bogies, the wire is pulled out of the oven and travels from there along the light railway track into the drawing mill. Now for a slimming course to keep the athlete's muscles in trim. In this coal drawing mill, the wire is drawn on modern, continuous, non-slip machines through tungsten carbide dies which reduce its thickness. Through a soap lubricant, the wire passes into the die. Threaded through this machine, it goes through 6 reductions, reducing in area with every die it passes through. Each wire must be reduced to the correct point consistent with strength, so that the finished cable should be pliable as well as strong. Here is a coil being tied up, ready for testing. To ensure continuity as the wire passes smoothly through the machine, the second coil of rod is butt welded to the first. So perfectly executed is this welding process that the weld passes easily without hitch or breaking through all the dies to be cut out in due course. And now another view of heat treating, this time heat treating and galvanizing in a continuous process. The machine draws the wire for galvanizing through a thermostatically controlled radiant tube furnace fired with Town's gas. The furnace is 22 feet long. The automatic control keeps the temperature between -5 and +5 of the standard required. The wire proceeds on its way through the acid bath, the water spill, the flux bath, into the bath of molten zinc. It emerges from the smelter through a charcoal wipe to give it a smooth, even coating of zinc. So on to the winding drums. And from there, back to the wire drawing machines for further reduction. This is yet another process, fine wire drawing through a wet soap solution. The girl is threading up 11 dies which work totally submerged in the wet solution. The dies, after wear, have to come out of the machines and go to the die grinding shop, where they're examined, opened out and recut to shape, and polished again, ready for use in the wire mill. At the bench, they are re-ground. A girl polishes them to the necessary finish with willow wood, coated at the tip with very fine diamond dust, rouge and other materials. This gives the die its high mirror finish. This automatic needle grinding machine was designed on the premises specially to grind the needles for opening the dies. A magnified view shows the die pierced and polished with a record of the number of times it has gone through the process. It has been in the mill many times at various sizes and has drawn 1,000 tons of wire. And so back to the wet drawing mill, where wire is being drawn to 0.0072 of an inch. Before it leaves the mill, the wire must be tested for reliability. First you see the bend test, then a torsion test on a gauged length, 100 times the diameter of the wire, registering the number of twists of which it is capable. In addition, the two ends of all the coils of wire are tested rigidly for tensile, elongation, gauging, wrapping, and standard specification of galvanizing in the case of the galvanized wires. All wires not conforming to specifications are rejected for reprocessing. At the ropery, the wire is subjected to similar tests when it arrives to make sure that it's up to the standard essential. In this dipping test, the wire end lies in copper sulfate solution for a given number of minutes according to the size of the wire. The tester examines it to see if the scepter coating is fully protective against corrosion affecting the steel. All ropes must reach a given standard of resistance to tensile, torsion and bends. This goal makes a tensile test to verify the strength of the material. This is followed by a group of ductility tests, including torsion, bending and wrapping, to detect any brittleness set up by maltreatment of the rod in drawing or any defects in the steel rod itself. The break of the tensile is recorded. The torsion test is usually taken on a length 100 times the diameter of the wire, and the number of twists varies according to quality. In the wrapping test, the wire is wrapped on and off itself until it fractures. Also taken. Thus, the ropery as well as the wire mill has satisfied itself about the strength of the wire for the purpose required, in this case for an excavator rope. From a store of wire which has been similarly tested in every particular, wire coils reach the winding department. A coil of wire goes on to a swift for winding. The tie bands are cut and the coil slides into position. This is an automatic winding machine. The end of the wire is threaded carefully into the machine. The wire is then carried onto the machine bobbin, ready for the stranding process. This is a particularly exacting job, as the bobbin must be evenly wound to suit the stranding machine and prevent slackness and raffles. If tangles or breaks occurred during the stranding operations, there would be a serious hold-up in the work and possibly considerable damage done to the carefully prepared steel wires. Naturally, the bobbin varies in size according to the type of machine which is going to be used. As soon as the bobbin is evenly and completely wound, it goes on a truck to the stranding department, where a variety of machines perform the actual task of spinning the individual strands of the steel rope. Stranding machines are either of the snake type or the sun and planet. Here, for example, is a big snake machine loaded with 19 wires of 3 different gauges. A wire in the center covered by 9 small gauge wires, covered again by 9 of a larger gauge. A bobbin of wire is loaded into the machine. There are 19 of these. They thread the wire along the periphery of the machine until ultimately all 19 converge through the lay plate to the twisting point at the compression guides. The foreman checks up and the machine gets going. The length of the twist is predetermined according to the type of rope required and is an essential feature of the laying up process. The finished strand proceeds over the capstan to the takeoff bobbin. The full bobbin of the finished strand is then taken out. There are similar snake machines of varying sizes. Here is another carrying 12 bobbins of wire. In contrast, a sun and planet machine running in triple formation. These 18 bobbins revolve round their center like a planet round the sun, but each bobbin remains in a vertical plane. They carry 18 wires to manufacture a 37-wire strand, which they effect by covering a 19-wire strand. This gives a clear picture of the fundamentals of the sun and planet. It also has a headpiece with lay plate on the same principle as the snake machine. Now on to a big closing machine. 6 bobbins of strand are loaded in, each of them consisting of 19 wires. The closing machine also is of the sun and planet type. The strands, similarly, are led down. The gear wheels are adjusted while the loading proceeds. The strands have been formed to a predetermined twist and direction. Here, the strands are preformed into the helix they will occupy when finally closed. The machine starts up feeding the strands into the compression dies. Emerges from the other side of the compression dies. The compression rollers are then put on to ensure perfect roundness of rope. Once more, the finished rope goes round the takeoff capstan and then reels onto the big wooden drum. Someone has to be at hand to ensure the even guiding of the rope onto the reel to avoid damage to the rope by crossing. And so the drum of finished rope is complete and ready to be taken away for dispatching. This closing machine has a capacity of 20-odd tons. This rope, coming onto the closing reel, is 4.5 inches in circumference, made up of 6 strands of 19 wires each of galvanized quality. From the closing machine, the rope goes on to have its desired fittings attached by splicing. In this case, the required fitting is a thimble splice. The rope is bent round to seize the thimble in, and it's bound tightly for the splicing operation. The splicer opens out the strands, and he inserts his marlin spike into the rope to open up and thread the strands through. The strands are tucked in and split to put in the last two tucks, thus ensuring that the splice takes a tapering formation. This man hammers up the splice to take out any slackness. The pincers then trim off the fag ends of the strand. After that, the splicing is parcelled to give a good seating to the serving. This follows with a soft galvanized strand wound on neatly to protect the splice and give a neat finish. The end of the serving wire is tucked under one of the strands to fix it, and there is the whole job finished. The thimble splice, eye splice and Bordeaux connection are only 3 of many possible fittings. Another is a hand-forged conical anchor socket. It's used, among other purposes, for straining guys for aerial ropeways. The socket is threaded onto the rope. The rope is opened out at the end and bent back. This cone is pulled back into the body of the socket, and the socket is adjusted with the cone lying so, ready for metaling. After heating and fluxing, the hot white metal is poured into the body of the socket over the cone, and this is the effect that is produced. On the finished rope, a destruction test is carried out. Tremendous strain can be put on it in use, and to make sure that the minimum specified breaking point has been obtained, a length of the rope is subjected to a severe and increasing pull. This rope is tested for breaking at 15 tons. Gradually, the weight behind the pull becomes insupportable. It passes breaking point. The destruction test is completed successfully, for the break was well beyond the estimated point. Every precaution has been taken, every skill used to produce a reliable rope. It is packed, stenciled with the firm's name, and sewn into a canvas cover as a protection. Finally, it is loaded onto a lorry, and off it goes to fulfill the order. And now, the rope in action. It has to be a sturdy and reliable one to operate this dragline excavator working on an open cast coal site. The tug-of-war with stubborn lumps on the job demands a rope as sturdy as the men who operate it and reliable as the men who made it. A rope. What could be more ordinary and everyday? So commonplace that you hardly notice it. Yet, how many and how great are the tasks it performs? How much depends on it, especially if it's a wire rope. It drags the bucket through unwilling soil. It raises and lowers the miner's cage. It swings heavy loads on the dockside crane with easy power. The power of many minds and hands transmitted by strands of steel.